Hey guys, so today's part two of graphing polar equations. Today we're going to talk about the ins and outs of how do I sketch a polar equation given what I know about r and theta. So we're going to go ahead and start today. First thing I want you guys to do is go ahead and put some partitions on here. We're going to go ahead and calculate out some values of r given that I know what theta is. So if r is equal to 4 sine of theta, what I want to do is figure out what the r values are. Well, if I plug 0 into sine, 4 times sine of 0 is the same thing as 4 times 0. So r must be 0 here. To plot this on the coordinate grid, we're going to be at an angle of 0 and a length of 0. So that's basically right here. Next thing we're going to do at pi over 6. That's going to be the same thing as me saying 4 times sine of pi over 6. If I remember what sine of pi over 6 is, it's half. 4 times a half is 2. So that means I'm going to go to the right 2, go to the right 2, and I'm going to go up pi over 6, like this. We're going to continue to do that. I'm actually going to continue to do this with you because it will get a little bit trickier. If we have pi over 3, I know that sine of pi over 3 is going to be radical 3 over 2 times 4. 4 times radical 3 over 2 is going to be 2 radical 3. 4 times sine of pi over 2. Sine of pi over 2 is 1, so that's going to be 4. All right, so this is where it gets interesting. 4 times the sine of 2 pi over 3. Well, sine of 2 pi over 3, actually, never mind, I take it back. It doesn't get interesting yet. We'll keep on going. All right, so 4 sine of 2 pi over 3. Well, sine of 2 pi over 3 is the same thing as the sine of pi over 3. It's radical 3 over 2, so we're going to get 2 radical 3. And then sine of pi over 6 is still a half, so we're going to get 2. And then sine of pi is 0. So now is where it gets interesting. Okay, so I'm going to go ahead and plot the points so far. At 2 radical 3, I think 2 radical 3 is the same thing as like 2 times 1.7-ish, so like 3.4. So this basically means like 3.4. I'm going to move my r to be like 3.4. That means I'm going to go to the right 3.4, 3 and some change, and I need to go up pi over 3. So maybe that looks like this. The next point is going to be at 4. I'm going to go length 4, and I need to go all the way up pi over 2, like this. The next one is going to be the same length. It's 2 radical 3, which is like 3 and some change, 3.5-ish or 3.4. And I need to do 2 radical 3. So that's right around here. And at 5 pi over 6, I'm going to be back at 2, like this. And at pi, I'm going to be back at 0. So you kind of see we've actually started to repeat at this point. So what's curious is what happens at 7 pi over 6. So sine of 7 pi over 6, that's on this line right here. Sine of 7 pi over 6 is negative a half. So this is where things get interesting. R is going to be equal to 4 times the sine of 7 pi over 6, which is the same thing as me saying 4 times negative a half, which is negative 2. Question is, what the heck does it mean for R to be equal to negative? Because r is a distance, so it doesn't really make sense that r would be negative. So we do have a fix for that. If I want r to be positive, say I have negative r, comma theta. To rewrite this, we learned this last section. We can write it as r, comma theta plus or minus pi, or we say absolute value, maybe thereof. Or it could be the opposite. It could be pi plus or minus theta, depending on what theta was originally. So what I'm going to do is I'm going to subtract pi from 7 pi over 6. So if I subtract pi from 7 pi over 6, that brings me back up to pi over 6. So to have a positive theta here, if I kind of extend the line, this is pi over 6. Pi over 6 at a distance of 2 is really just a repeat point of pi over 6 comma 2, or 2 comma pi over 6. So what we can see here is that when we have a negative r, we do need to do a little bit of math acrobatics to kind of switch it up. A negative r can be switched really easily by either adding or subtracting pi. And so you're actually going to see that for the next one too. The next one's going to be negative, the next one's negative 4. And then the next one I think is negative, I might have, nope, I think that one, yeah, still negative 2. And where's over 3? Did I miss the over 3 one? Talking to myself here. Maybe I did. Okay. Anyway, we're going to get negative values here. So once again, this negative 2, 11 pi over 6, comma negative 2. That's going to be over here this time. but I don't know what really a negative r value means. So what I could do is I could add or subtract pi from it. So if I add or subtract pi, I actually move back up to this point here. So we can see that this point, 11 pi over 6 and negative radical 2, they're kind of repeat points of these 2 points. So they're kind of repeats once again. So kind of just keep in mind that if you have a negative r, you're probably going to have to add or subtract pi. All right, let's keep it moving. All right, so there is something that's called symmetry of specifically polar functions. So we can see that the symmetry of a polar function, it's the same thing as the symmetry of a rectangular function. The first graph that we see here, if I go ahead and connect the dots, we can kind of see that in rectangular form, we'd say it was symmetric with respect to the y-axis. But this isn't rectangular form, this is polar form. So we'd say it's symmetric with respect to the line theta is equal to pi over 2. Or we could say theta equals 90 degrees. So that's one type of symmetry. Another type of symmetry is if it's symmetric with respect to the polar axis, which is kind of like the x-axis. And the last one you're not going to see so much is going to be symmetry with respect to the pole, which is kind of like symmetry with respect to the origin. So taking a look here, there's just some basic information regarding symmetry of polar functions. Okay, so let's go ahead and talk more about this. More specifically, if something is symmetric with respect to theta equals pi over 2, you can replace r and theta with r comma pi minus theta, or this one's my favorite because it's easier, negative r comma negative theta, and you're going to get the exact same answer. So this is kind of like when we maybe talked about in Algebra 2, when something is symmetric with respect to the y-axis, you can replace all of the x's with negative x and get the exact same thing. So here are some general rules. We're going to come back to them in a minute. Just know that they are here. Let's go ahead and talk about our next example. So we're going to use symmetry to sketch the polar graph. Okay, so the first thing we're going to do is we're going to start off with a table. Specifically, if I want to run a test of symmetry, I can take the equation r equals 3 plus 2 cosine of theta, and I can check and see if it's symmetric first. Let's try the first symmetry. Let's see if it's symmetric with respect to the line theta is equal to pi over 2. If that's the case, then I can replace r with negative r and theta with negative theta and get the same thing. So let's do that. Negative r is equal to 3 plus 2 cosine of negative theta. Well, I know according to properties, this is actually an identity. Cosine of negative x is the same thing as cosine of x. So this reduces to negative r comma is equal to 3 plus 2 cosine of theta. That's not the same as my original starting function, so that symmetry doesn't work. The next symmetry I'm going to try is the polar axis. If I replace r with itself, r, and theta with negative theta, let's see if we get the same function. Well, using that identity here, I know that cosine of negative theta is just the same thing as cosine of theta. So we're going to get 2 plus 2 cosine of theta. So this one works. We can see it's symmetric with respect to the polar axis. Because it's symmetric with respect to the polar axis, that means all of the values that are in the first and second quadrant are going to reflect to the third and the fourth quadrant. So because of that, I really only need to check quadrant 1 and 2, which means I'm only going to check the values 0 through pi. So if you go ahead and copy this down here, you can pause the video if you want. If we go ahead and copy down these values, the only thing we really need to plot are the points between theta is equal to 0 and theta is equal to pi. After that, it's just going to be repeats because we have symmetry. Well, there'll be repeats, but there'll be negative reflections. All right, let's keep on moving. We don't have to focus too much on this. Just know that there are some graphs in polar mode that are not going to work with the symmetry test. This is an example of one. But for the most part, if you do run into these, there are some special formulas. This might just apply if you're doing this on your project per se, but we'll keep moving on this one. Okay, this one, I don't know how important this one is to, but I'll talk about it anyway. If you take the composite function of f and you put sine inside of it, it's automatically going to be symmetric with respect to theta equals pi over 2. If you compose cosine into a function, it's automatically going to be symmetric with respect to the polar axis. All right, so sketching a polar graph. We want to sketch the graph r is equal to 1 minus cosine of theta. Well, using one of our tests, we can say, let's say we replace r with r, and we replace cosine with negative theta. So we say 2 cosine of negative theta. Well, this reduces to just r is equal to 1 minus 2 cosine of theta, which is the same thing, which means this is going to be symmetric with respect to the polar axis. So I'm only going to check the values 0 through pi. Go ahead and see if you can fill out the remaining information on this table. You can pause the video if you want. Okay, so hopefully you guys have had a chance to fill out these values. So let's go ahead and see what you should have in your table. Okay, so these are the values that we should have. Note here that we have 0, -1. If r is equal to -1, we kind of have an issue here. So I'm going to actually take the ordered pair -1, 0. And in order to turn it so that it is no longer negative, I can say that it's 1, pi instead. So I'm going to say 1, pi instead. And that's going to lead me to my first point, which happens right here, 1, pi. Same thing here. This is also technically a negative value. We could think of it as like -0.7, pi over 6. If I want to make that positive, I can make it into positive 0.7, pi over 6 plus pi. It's going to be 7 pi over 6. So we're going to have positive 0.7 at 7 pi over 6, which might kind of look like maybe this point right here. So if you go ahead and fill in all of these points, it's going to go in this order, like here, and should end this way. So it's going to kind of loop in. This is called a LAN. I cannot think of the word right now, and I will think about it later. Okay, so some things that I want to kind of talk about here. The maximum value of r. So the biggest that r possibly gets, if we just look at our table, is r gets to be 3. So the maximum value of r is 3 when theta is equal to pi. Some other things that I know are 0. So when does it cross that polar axis? It's going to cross the polar axis when r is equal to 0. So we can see that when r is equal to 0, and when theta is equal to pi over 3. So we can kind of see that maybe like right around here. Okay. I think that is all that I want to cover on this one. This is called a limicron, by the way. All right, next one. It says sketch the graph of r equals 2 cosine of 3 theta. Well, first thing, if I run a test on this, we can say that r is going to be positive, and we could make theta negative. This is cosine of -3 theta, which we're going to see it should have some symmetry across the x-axis, or we would say the polar axis, because the property here is that it would reduce to being the same thing. So if we want to think about some variables that we should test, we probably should test between 0 and pi for sure. And in fact, we might be able to figure out a more systematic way to figure out variables to test. So because I know it's symmetric with respect to the polar axis, I know it should be between 0 and pi. So basically, I know my thetas that I need to check are going to be between 0 and pi. Except it's a little more complicated than that, because theta is not just theta in this case. Theta is actually 3 theta. So I'm going to change this to 3 theta. I'm going to change this to 3 theta, okay? Okay, so because I'm checking now, instead of thinking of theta as being just theta, we're thinking of theta as being 3 theta. Well, let's think about the typical candidates we're going to test. We usually are going to test 0, pi over 6, pi over 3, pi over 2, 3 pi over, nope, I always do this wrong, 2 pi over 3, and 5 pi over 6, followed by pi. Well, because we're actually talking about theta here, right? So this is equal to theta. But we know that theta isn't just theta. Theta is actually, in this case, 3 theta, right? So this is all 3 theta is equal to all of these things. Well, if I want to reduce that so I know just about theta, what I can do instead is I can divide everything by 3 and figure out what is just theta by itself. So 0 divided by 3 is 0. Pi over 6 divided by 3 is pi over 12. Pi over 9. Pi over 6. 2 pi over 6. So we'll have 2 pi over 6, which is the same thing as pi over 3. 5 pi over 12. And then pi over 3 again. So we have some repeats here. We also have some values that we just don't have on our scaling quite as easily, like pi over 9. So I'm going to get rid of that one just because it's going to be hard to graph. So some better scaling things that I could check are probably going to be between 0, pi over 12, pi over 6, pi over 3. And if we're going between still 0 and pi, we probably want to have a couple more values in between. So we can still check pi over 2 and okay, so maybe some better scaling if we kind of put all of this together. It could be between 0, pi over 12, followed by, let's say, something in between, so like pi over 6. I don't have pi over 4 in here, so I'm not going to check that one. Pi over 3 would probably be another good one to check. Pi over 2 is probably a good one to check too, just because we're going to be between 0 and pi. And we could also probably check 5 pi over 12. So we can probably check all of those. All right, so what I want you guys to do, go ahead and fill out the table for the following values, and then we're going to graph. So go ahead and fill out the table. If this is theta, go ahead and find r. Okay, so this is what we should get. So what we're going to do is just from start to beginning, we're going to go ahead and see what happens as we graph this. So I kind of already have the graph here, but we're just going to kind of graph it systematically. All right, so first thing we're going to do, at theta is equal to 0, r is 2. So looks something like this. So at theta is equal to 0, r is 2. From there, at pi over 12, which is going to be somewhere in the halfway mark, it looks like we got radical 2, which I don't know, is like less than 1. So maybe something down here. From there, at pi over 3, which is going to be a little bit up, it's negative 2. So think about it like this. If I have negative 2 comma pi over 3, if I want to make that positive 2, I could add pi to it. So if we add pi to that, we're going to get 4 pi over 3. So I'm going to really be looking at 4 pi over 3 comma 2, which is going to be down somewhere like this. So what I'm getting so far is maybe something that looks like this. All right, so from there, I'm going to actually connect. I'm going to kind of show you the curvature of this. We're going to connect like this and like this. And then from there, we're going to go back up to 0 at pi over 2. So we're going to come back up to 0 like this. And then from there, we're going to go back out. And we have another negative this time, 5 pi over 12. I'm actually just going to sketch this one for you because it's going to be a little bit kind of harder to see here. But it is going to sketch up somewhere around here. And then it's going to sketch down and sketch one more time. You might be wondering, okay, Ms. Johnson, how do you know this is happening? Well, the real point of this exercise is not necessarily that we'd be able to do all of these by hand all of the time, but I did want you guys to kind of see the pattern here, and I do want to show you how to do this on your calculator. So the next thing I want to show you is what's this going to look like in the calculator. If you press math and make sure that you are in polar mode. So scroll all the way to polar, make sure it's highlighted. Also make sure you are in radian mode. Select y equals, and we're going to go ahead and graph this and see how it graphs. So we're going to say 2 cosine of 3 theta and graph. I know it did it so fast, your graphing calculator might have been a little bit slower, but it should follow this method. So let me get my, oh no, there we go. Let me get my pen out. And let me see if I can draw kind of like the pattern of what's happening here. So here's what's kind of happening. It's going like, is it going to let me draw? Nope, I'm going to have to screenshot it. Okay. Let's screenshot this. Okay. Okay. All right, so here's what's happening. So this is actually what's called a rose. It's like official name of what the shape is here. Here's what's happening if we talk about like order. So I'm going to start kind of here. At 0, I'm all the way up to 2. From there, I'm going to move in this direction. So from there, I'm going to move in this direction. From there, I'm going to continue to move down like this. And then I'm going to sweep back up like this. And then I'm going to sweep back up again like this. Sweep back down, and then come back all the way back to where I started. So that motion is kind of important here, but notice it kind of starts over. It kind of starts itself over by the time that we get back to the beginning. So it kind of has a range, if we're thinking, it kind of has a range of pi over 2 at max. After pi over 2, it basically starts over, which kind of makes sense, maybe a little bit less, but that would be the graph right here of the rose function, which is 2 cosine of 3 theta. Okay, so all I'm going to talk about next is just some basic types of polar equations that make some pretty cool looking shapes. So the first one we start off with are the limicons, or I think it's just limicons. I don't know what the little C does. I'm sure it pronounces differently. So these are just some basic equation types that are going to help you to create given shapes for your project. The rose curves, those are my favorite. So if you ever, I know prom season is coming up, these ones are a real class act. They're a real favorite. What's interesting about the rose curves is that if you have n being odd, then n represents the number of petals. But if n is 2n, so say we have 2n petals when n is even. So basically, you're going to, like, for example, in this one, if n is equal to 4, then n in this case would be like, I guess the number of petals is going to be twice that, which is 8. So 1, 2, 3, 4, 5, 6, 7, 8. But if n is 3 here, it is what it looks like. It's just 1, 2, 3. So it's an interesting pattern. I think it's really fun. You can kind of mess around with that on your calculator as needed. Last one are circles and lemniscates or something like that. So these are all some examples of very interesting looking polar equations that you guys can potentially use on your project in the future. So the last thing I want you to do is take a look at the requirements of the given project that you have. And what I want you to do is just kind of sketch out in your brain, what do you want to do with your project, and what kind of equations do you want to create whatever image you're working on. So if you have any questions, of course, ask me a question. I'd love to get back to you. And hopefully I can answer your questions in person very, very soon.